So we calculated the bed load transport for our channel in the last video. We're now going to enter the section for suspended load transport for this specific channel. Remember, this is a very special channel that gave us three very different values for bed load transport. Generally, it's not the case, but when this happens, it's up to you, the engineer, to figure out why this happened and to choose the value that most closely approximates what's really going on. In our case, we chose the Mayer-Peter result of 0.00024 meters cubed per sediment per meter per second. So this value of bed load transport is key to calculate our suspended transport magnitude. This is the total equation, H over 0.33 Ks, where Ks, as we mentioned in our booklet, is 100 times our D50. Then plus I2. We're going to go through each step to calculate the suspended load in this channel so you understand basically what are the steps to do this. The first step, of course, is start with the first unknown. What is the first unknown? We have I1. What does I1 equal? Well, according to our packet, it's a very complex integral that Einstein worked out. Z star minus 1 over 1 minus A Z star times the integral of A to 1 minus B over B dB. You will need A times to the power of Z star. Z star is a very important parameter, as we see throughout this equation. So we don't know that, so let's go ahead and calculate that. So for Z star, what does it equal? It equals the falling velocity divided by the von Karman constant divided by the friction velocity of the channel. We know this from the past. Nevertheless, we do not know the falling velocity. The falling velocity is equal to a very rather complex equation that we mentioned in a previous video. And it is basically very long equation, but it works. 36 excuse me equals, and then we have a ratio. We have 36 looks pretty scary, but the falling velocity of the particle is this big long equation right here. Now, the beautiful thing about this is that we know all the parameters that this equation asks. Kinematic viscosity 1 times 10 to the negative 6 meters squared per second. S is 2.65. G is 2.91 and D50 is 0.2 millimeters. Putting everything in gives us that the falling velocity is equal to 0.0207 meters per second. With this, now the next step is to calculate U star. We don't, we have actually not calculated U star. We have calculated the U star for effective conditions, but for this formula we need the U star for total stress conditions. So U star is basically square root of T over rho, which is basically square root of 13.7 newtons per meter squared divided by 1,000 kilograms per meter cubed. That means that U star is equal to 0.0 meters per second. We have U star, we have W star, which should be W star here, and now we have all that we need to calculate Z star, because we know that K equals 0.4. So if we use these three results here, we get that Z star, very important to get it right, is 0.442. So that's a good first step to start our I1 equation. So I'm going to erase everything. Now that we figured out what our Z star was, trying to go step by step here. Which this. So I'm going to write it here. Z star is equal to, as we said, 0.442. That means we know what to put here, what to put here, what to put here. Next step is to calculate A. A, it's a simple calculation. It's just the roughness, Ks over H. This is 100 times our D50, you know this, times the divided by 5 meters. And this comes out to be 0.004. So we know A. I'm gonna simplify it. A equals 0.004. We have everything we need to calculate this integral. My first suggestion is that you go ahead first and simplify this whole term here. If you do that, you will come up with 4.71 here. Now the integrating part. This can be done in your TI calculator, and you basically plot in your Y formula. Let's replace this dB with an X just for familiarity purposes. So you go ahead and plot this equation to the power of Z star, and then you use the option. You have to integrate the lower boundary, A, 0.004. The upper boundary is 1. So if you do this integration in your TI calculator correctly, you should get this times this, you get 1.32. And when you multiply this together, you get 6.21. So good job. We have figured out what I1 is. So 6.21. I'm gonna now erase everything just to have I1 alone up here. That is the first step. 6.21. So H, we know, KS, we know, I2. Next step, we're almost there. I2. What does that equal? According to Einstein, the I2 formula is actually very similar to the I1 formula. I'll copy it again for clarity purposes. Yeah, the only difference I2 has with I1 is this ln to the b term. So what do? Go into your I calculator and multiply this function times ln of b, and then integrate from the same boundaries as we did before, from 0.004 to 1, and you should get a value here that is equal to negative 2.40. Look at this value here in the front, this value here in the front. It's the same one we calculated in the beginning. This is 4.71. Multiply them together. What do we get? We get negative 11.3. So voila, there is our I1 and I2. Let me erase. Let's continue. I1, I2, 11.3. Let's go ahead and calculate our suspended load transport. So I think we should have enough space here. 1.83 times our bed load transport, we said 0.00024 meters cubed per meters per second. Here, I1 6.21 times ln of H is 5 over 0.33 times our roughness is 100 times D50, so what it is 0.02, right? 100 times 0.0002 is this. Close parentheses, plus I2, we have a negative. Voila, we have everything we need to calculate the suspended transport. If we plug this carefully into our calculator, we should get that the suspended load is 0.194 meters cubed per meter second. If you get this number, congratulate yourself, because it was a hard process to get here. The total sediment transport is, what is it? Well, is the bed load plus the suspended load. Look at this, we know both of them through the Mayer-Peter approach, of course. And this, since our bed load is very small, in our case, this does not change our final result by much. As you can see, from here to here, this is the total load that we would expect. One important final remark is the ratio between the suspended load to the bed load. There's always going to be substantially more suspended load than bed load in any channel. In our case, this ratio is 77.6. Very, very large amount of suspended load relative to bed load. So now, I hope you understand a little bit better what the formulas in the booklet are trying to tell you, and the process on how to calculate effectively everything that you need. And that is all for the video. Thank you very much.